morning, crew. Well, it's morning for me, pretty early morning, still dark outside. It's probably not morning for you, but welcome anyway. We are talking about quadratic functions today, and specifically about the features of the graph of a quadratic function and how we can use those features to learn something about a situation that can be modeled by a quadratic equation. Tomorrow we'll look at how to write a quadratic equation or a formula for a quadratic function, but we'll save that for tomorrow. Today we're going to stay focused just on our features. So let's start here with our formulas for a quadratic function. Like formulas for a linear function, we have different forms. We have standard form, which you're familiar with, which is y equals ax squared plus bx plus c. A can't equal 0 because then you wouldn't have a quadratic form. So again, this is pretty form, right? Prettier presentation form. We have factored form, which I also call the intercept form. Right. So factored form looks like y equals a, this is the same number for the same quadratic, times x minus some number times another factor of x minus another number, where those numbers, r and s, are your x-intercepts, thus the intercept form. And finally, the vertex form, which is y equals a, same a, times x minus hk, where the numbers h and k give us the vertex of the quadratic. So obviously, why it's called the vertex form. The other thing we have is the quadratic formula. The quadratic formula will find the solutions to when f of x equals 0. So it only makes sense to use after you set a quadratic equal to 0, and you know that quadratic formula, right? We've used that several times this year already. So there's that. Features of a quadratic, right? So the graph of a quadratic looks like a parabola. So we might have a happy parabola or a sad parabola, right? So it might be happy, might be sad. The vertex is the turning point of the parabola, so this would be my vertex, hk. We have a formula for finding the vertex, and that is that the h is the opposite of b over 2a, right, when we have our quadratic in standard form. I could give you a formula for k, but it's pretty complicated. It's easier just to say k, which is the y-coordinate of the vertex, you can find by taking h and plugging it into your function, right? So I have my vertex hk. My line of symmetry is the line that's going to divide that parabola in half, and that line would go right through the vertex. So it will have the equation that is x equals the h coordinate of that vertex, the x coordinate. So that line of symmetry, it always will be x equals h. The y-intercept will always be what y is when x is 0, right? So the y-intercept c can be found simply by plugging 0 in for x. Your concavity, I think we've mentioned concavity this year, is up if your a is positive. So it's concave up, it's going to look like part of a bowl, happy parabola. Concave down if a is negative, right? It's going to be a sad parabola, negative people are sad. Our domain is negative infinity to infinity unless we're limited by circumstances, which when we do modeling is often the case. And our range will be k to infinity. So if this is my parabola and I have my vertex, say at, say my vertex was at 2, 3, then I have points that reach a low of 3 and then go up to infinity. So that would be my range. If I had a sad parabola, so if this is the point 2, 3, right, then I have points that go from there down. So that range would be from negative infinity up to k when a is negative. All right. So those are my features. Now let's use them. Here's an example. We have a high diver that jumps off a 10-meter springboard. For h in meters and t in seconds after the diver leaves the board, her height above the water is given by h equals f of t equals negative 4.9 t squared plus 8t plus 10. So when we read this equation, we can see that our A is equal to negative 4.9. So our A is less than 0, which means that we're going to have a concave down parabola. So if I'm going to graph this, I'm going to have an h-axis, right, because this is finding height. I'm going to have a t-axis because my independent variable is t. I know it's going to be a sad parabola. The other thing I know is that if I take 0 and plug that in for t, then I get negative 4.9 times 0 squared plus 8 times 0. So both those terms are 0 plus 10. This constant in the equation gives me my h-intercept. So if I'm going to graph this equation, I know that it's going to hit the y-axis at 10, and I know it's going to be a sad parabola. So kind of like to find where that turns around. Well, we can find where it turns around by finding h. So if I want to find h, I know that h will equal negative b over 2a, which for this, right, 8 is my b, so that'll be the opposite of 8 over 2 times a, right? A is negative 4.9. So negative 8 over 2 times negative 4.9. And if I simplify that, I get 0.816. So that tells me the x-coordinate of my vertex. If I want to find the y-coordinate of my vertex, I'm going to plug this number into my function. So I'm going to find f of 0.816. So that would be negative 4.9 times 0.816 squared plus 8 times 0.816 plus 10. And I used my calculator to help me evaluate that, and I got it correct. A 3 decimal place, 13.265. So I know that, let's say if 1 is here, then 0.8 would be somewhere around here, and if this is 10, then 13.265 is going to be somewhere around there. So at that point, right, I have, right, 0.816, 13.265, that's a 13. I have my vertex, so I know my parabola will rise to this point, and then it's going to turn and fall. So the question I have is, where does it cross that t-axis? Well, I can find my t-intercepts by, right, so I'm going to find my t-intercepts by setting my quadratic f of t, which is negative 4.9 t squared plus 8t plus 10 equal to 0 and solving that. I can solve that through factoring or with a quadratic formula. Because I have a decimal in there, and to clear that decimal I'd have to multiply everything by 10, which would make my numbers pretty large. I think I'll go ahead and use the quadratic formula here. So I get t equals the opposite of b plus or minus the square root of my b, which is 8 squared, minus 4 times a, negative 4.9, times c, which is 10, and all of that goes over 2 times negative 4.9. I evaluate that, and again, I did that with the help of my calculator, and I got two numbers, right? One from subtracting, one from adding, and those were negative 0.829 and 2.462. So I now know that where this crosses the t-axis must be at 2.462. What's this negative 0.829? Well, if this parabola extended to the left, then where it would hit on the left side would be negative 0.829. Not relevant for our diver, because the only thing we know about her height, right, is that it follows this function as long as she's in the air. So we have a lot of features that we found here. Let's go back and see if we've answered the questions. Okay, our job is to find the domain of the function, the range of the function, right, and the intercepts of the graph. And not only are we to find them, but we are to interpret them. All right, so let's see if we can do that. Okay, so let's start with our domain. Okay, the domain of our function is the smallest t to the largest t that fits this situation. Well, that's just going to be from the moment the diver dives off the diving board until she hits the water, which is going to be here. So our domain is going to be from 0 to 2.462. Right? What does that tell me about my diver? Right? So she is in the air for 2.462 seconds. I want to find the range of my function. So the range of my function is my lowest height to my highest height. Well, the lowest height she reaches here, right, on this part of the graph is 0. The highest height she reaches is at the y-coordinate of the vertex. So the range is 0 to 13.265. Right? So, and that tells you that, that she reaches a height of 13.265 meters above the water. Okay. So that's our domain and range. Our intercepts we've actually already found. So we come in here and we had our h-intercept we found by plugging 0 in for t, right? And that was 10. So our h-intercept was h equals 10. Right? And that tells us that she jumps from 10 meters above the water. That's where she starts. And then finally we want our t-intercepts, and our t-intercept we already found as well. So our t-intercepts we found by setting our function equal to 0 and using the quadratic formula. And the one that makes sense, that fits in our domain, is just this 2.462, and that would be seconds. And that tells us that she hits the water, right, after 2.462 seconds. So there we have math, and we have math applied. Let's look at another example. Okay. So we want to determine the features of this quadratic. So let's come in and review what our features are. So we want to find the vertex. We want to find the line of symmetry. We want to determine the concavity. We want to find the domain. And we want to find the range. And then we're going to draw the graph. All right, so if I want to find the vertex, I know, right, so I'll do my work here. I know that h will equal the opposite of b, so the opposite of negative 12 over 2 times a, so 2 times negative 4. So that gives me positive 12 over negative 8, or negative 3 halves. I know that k, I'll find by plugging -3/2 into my function, which is called t. So I find t of -3/2, right? And if I put that in where x is and I work that out, I get 1. So that tells me that my vertex is at -3/2, 1. Okay. My line of symmetry is always at x equals, right, and my variable is x here, the h coordinate of my vertex, so that's going to be x equals -3/2. My concavity is determined by my value of a, so because a is less than 0, this will be concave down, so it'll be a sad parabola. My domain is not limited by anything, so I can use anything for x, and my domain would be -infinity to infinity. My range for a concave down parabola, right, is going to be from -infinity up to the y-coordinate of my vertex, so up to 1. So when I want to graph this, oh, you know what I haven't found? I haven't found the x-intercepts. Let's add that because that's really important. So I want to find my x-intercepts, right? I also need my y-intercept. Y-intercept is easy. It's the constant in the function, so that is -8, and let's say this right. It's not a y-intercept here. It's a t-intercept. To find my x-intercepts, I want to come in and I want to set my equation, which is t of x, which is -4x squared minus 12x minus 8 equal to 0. Well, there's a GCF here, so if I factor out a -4, that gives me another factor of x squared plus 3x plus 2 equals 0. Pretty sure that's factorable, and that would factor as x times x and 1 times 2, and if those are both positive, my outers 2x and my inners 1x give me 3x. So I set each factor equal to 0. -4 will never equal 0. It's always -4, so there's no solution from there. X plus 1 equals 0. Gives me x equals -1. X plus 2 equals 0. Gives me x equals -2. So my x-intercepts are -2 and -1. So if I go to graph this, looks like I'm going to need this. This is my t-axis. This is my x-axis. And if I take an x of -1, an x of -2, and then I need a y of 1. If I make this y 1 here, I know that I have a point at -3/2, 1, so that would be about there. My line of symmetry is going to go right through that number, so at x equals -3/2. Let's come in here and get a little bigger. So we were at -3/2, -1. I had x-intercepts at -2 and -1. I have a t-intercept at -8. Oh man, didn't make that big enough. So I wonder if I can grab this. No, that's all together. So let's regroup here. About that well enough, so I'm going to graph. Here's 1, here's -1, 2, 3, 4, 6, 7. Here's -8. I'll make this -1 and -2. So coming back again, I have vertex at -3/2, 1. I have x-intercepts at -2 and -1. I have a t-intercept at -8. I have an axis of symmetry, at x equals negative 3/2. So I go to draw my graph, and we're going to get this sad parabola that comes down here. And because there's a line of symmetry, if this negative 8, right, if this t-intercept is 1.5 units to the right of the line of symmetry, then if I go to 1.5 units to the left, I would have another point, and this is going to come right through there. Okay, so there's my graph. One more example. We're going to skip this example and go to example 4. In example 4, we're supposed to use algebra to find the maximum height reached by a baseball and the time which it reaches the ground, where the height of that baseball follows this function. So if I want to find the maximum height, right, I want to find the max height. Because my a, which is negative 16, is less than 0, I know the graph of this function is going to be concave down, which means the maximum height is going to happen at the vertex. So I want to find my vertex. Well, I know that h will equal the opposite of my b, so the opposite of 64 over 2 times my a, so 2 times negative 16, which gives me 2. I know that my k will equal f of 2. So when I plug 2 in for t and work that out, I end up with 67. Right? So my vertex, right, my vertex is at the point 267. And what this tells me is that after 2, t is in seconds, after 2 seconds, the ball reaches a maximum height of this number, right? 67, and height is in feet, so this is feet. So we found the maximum height, and we want to find the time at which the ball reaches the ground. So we want to find t when the ball reaches the ground. Well, we have information about height, right, which is our f, our y, and time, which is our t. So what's going to be true when the ball hits the ground? Right? So the ball is going to hit the ground when the height, which is f of t, equals 0. So I want to find t. I need an equation with t in it. Well, the height is negative 16t squared plus 64t plus 3. And I want to find the time that would make that equal to 0. And we know that we can do that by factoring, but I'm pretty sure this one's not going to factor. So we're going to use the quadratic formula, and this equals 0, so we can use the quadratic formula, and it will equal the opposite of our b plus or minus the square root of our b squared minus 4 times our a, negative 16, times our c, which is 3, all over 2 times our a, negative 16. And I play that out, and I get 2 numbers. I get negative 0.046, and I get 4.046. Right. Well, time doesn't start until after I hit the ball, so maybe I'm going to hit the wall here, but so this time is not in our domain. It would be after 4.046 seconds that the ball would reach the ground, right? So the answer to that question is the ball reaches the ground, right, or hits the ground after 4.046 seconds. Okay, so there we go. I'm pretty sure you've done all this before, but you do want to know the features of these quadratics and be able to use them to answer questions about a quadratic model of a situation.